Here we're going to look at the angle of twist, which is given a shaft like I have here, okay, different torquings and things like that. Basically, how much will it twist, given how far down the x-axis, the longitudinal axis it goes, and things of that nature. So that's really what we're looking at. So we're going to look at a little disk, just like we did with the torsion formula, at some arbitrary distance x away with a thickness of dx, and you get a shearing going on like this. Now, if you remember back when we talked about this little line right here is gamma dx, which is the shear strain times the thickness of the infinitesimal, okay? And that line also equals rho d theta, where d theta is actually the angle of twist I'm looking at, and rho is essentially the radial distance away from the piece that I'm actually looking at. So I have rho d theta equals gamma dx. Hooke's law tells me that gamma equals tau over g. Okay, so you remember that for shear, Hooke's law. And then the torsion formula is the torque times the radius, rho, over the polar moment of inertia. So again, we've had all this previously. So we're just going to manipulate these equations a little bit differently. So we're going to take this first equation and solve it for the angle of twist, or the infinitesimal angle of twist, just rearranging, bringing rho to the other side like I have here. Now I'm going to use Hooke's law and plug in tau over g in for gamma. Okay? And then I'm going to take the torsion formula to relate that to the torque. So I have the torque times rho over jg, all times dx over rho. So the rho's cancel, and I'm just left with this equation, and this is my angle of twist equation. Again, I'm just integrating both sides to find my angle phi that I'm looking for. That's the angle of twist. Again, I'm going to go from 0 to L, wherever I'm interested, in the total length of the twist, given the length of the rod. Okay, and that's going to be TDX over JG. And again, torque, J, G, they can all be a function of G of X. G oftentimes is not, but my torque can change as a function of X, and my cross-sectional area can easily change as a function of X, so the polar moment of inertia would change as well. Okay. However, a lot of times we have a constant area, we have constant torque, at least between discrete torques or discrete areas. Okay, so a very common use of this is to find phi. G is also constant almost every time. Okay, bring that out, and I get TL over JG. So that's the angle of twist for a constant torque, constant cross-sectional area shaft. Okay, now just like we did when we did the deflection of tension compression of axial load. Okay, if I have abrupt changes, that would be in between these two torques, or if I have an abrupt change in the cross-sectional area, or I've got two materials welded together. Okay, between those abrupt changes, I have constant. Okay, so I can do that. I just add up the total angle of twist. I find the angle of twist for each section, then add them up to find the total angle of twist, just like I did with the PL over EA equation that I had previously. Now, there is a sign convention. What I'm more concerned with is whether or not you follow a sign convention, at least keeping track of relative direction. So, for example, in this problem, T1 and T2 are in the same direction. T3 is in the opposite direction. Okay, but our sign convention is that the torque is positive when, using the right-hand rule, my thumb points out of the shaft. So if my thumb points into the shaft, we call that a negative torque. And again, if I cut a section on one side, my thumb will point out. On the other side, it'll also point out. Again, to balance, Newton's third law tells me equal and opposite, right? Okay. But again, the way it's gone is my thumb is pointing out from the cut side of the shaft. So that's what we're calling a positive. My thumb points into it, we call that a negative torque. So that's the sign convention used. But again, what I find more important is just recognizing relative directions. One torque's in one direction, another torque's in a different direction. Okay, so that's the angle of twist. This is the most important, TL over JG. So you remember that to determine the angle of twist given the torque on a shaft.